All right. Welcome back. So the fifth and second to last. We're getting close to the finish line here. Lecture by Jacob Lurie, this time about p-adic Hodge theory.
All right, thank you very much. So this lecture, I want to reset a little bit. Let me go back to something that we talked about in the first lecture. So, over the complex numbers, let's say X is a smooth projective variety, and some very basic form of the Riemann-Hilbert correspondence is that there's an equivalence between the category of local systems of complex vector spaces on X and algebraic vector bundles with a flat connection. So I'm a little hesitant to call this a Riemann-Hilbert correspondence because it doesn't seem to really engage with what I think of as the hard part, which is what to do about singularities, how to study algebraic differential equations with singularities. This is a situation where there are no singularities, and the equivalence is just a bit of differential geometry that says local systems of complex vector spaces can be identified with holomorphic vector bundles with flat connection. And then Serre's Gaga principle, which tells you that any holomorphic vector bundle has a unique algebraic structure since X is projective. So this is a story over the complex numbers, which is a relatively easy story. But what I would like to talk about in this lecture is what happens if you try to replace the complex numbers by a p-adic field like QP. And then this story becomes much more subtle. So let me just set up some notations. So K is going to be the fraction field of a discrete valuation ring. I'm going to assume that K is characteristic 0, the residue field is perfect of characteristic P, and that the valuation ring is p-adically complete. So that's equivalent to saying that K is a finite extension field of something that looks like the Witt vectors of a perfect field adjoin 1 over P. And an example would be K could be the p-adic rational numbers. But I encourage you not to assume that, not because it's not an interesting case, but because it's in some sense too interesting. So I'm going to be talking about Galois representations of K. And if K is a local field like QP, the theory of Galois representations has a lot of special features like local class field theory and Tate duality. And those special features are not going to feature in this story. And so the goal is to say something about p-adic local systems on smooth projective varieties over K. And something that I mentioned before is that when you're working over a non-algebraically closed field, the theory of local systems becomes interesting even when the variety is 0-dimensional. So in lecture 2, we talked about the case of a perfect field of characteristic P, and there the theory of local systems was a little bit interesting. But now we're going to be talking about a p-adic field, and the story is very interesting. So most of the lecture is going to be about the case of a point. So let's fix an algebraic closure of the field K. I'm going to write G for the Galois group. And then just concretely, a QP local system on X, you can think of as a finite dimensional vector space over QP, which is equipped with a continuous action of the Galois group. And these form a category, and we would like to understand that category. So let's recall in lecture 2 how we did this in a simpler situation. So let's say little k is a perfect field of characteristic P. We talked about this equivalence of cats, finite dimensional representations of the Galois group on vector spaces over FP can be identified with linear algebraic data, namely a K vector space with a Frobenius semilinear automorphism. And the construction that implements this equivalence is easy to describe. If you have a Galois representation V, you tensor it with the field K bar, and then you just take the invariance with respect to the Galois group, which is acting on both tensor factors. So now let's think about situation over a p-adic field instead. So you could do exactly the same construction if you wanted. So let's say you start with a representation of the Galois group on a QP vector space now. You could tensor that representation over QP with the algebraic closure of K and take the G invariance inside there. And what you're going to be left with is some vector space over K. And it's not hard to convince yourself that this is going to be a finite dimensional vector space. In fact, the dimension is going to be bounded above by the QP dimension of the representation that you started with. But you'll almost never have equality. You should think of this as a construction that almost always gives 0. So just could ask, what's the difference here in this situation versus the situation that we had 2 weeks ago? Well, in both cases, we're studying continuous representations of some Galois group, but the meaning of the word continuous has changed. So earlier we were talking about continuous representations on vector spaces over FP, and FP had the discrete topology. So continuity of the action meant that every vector was stabilized by an open subgroup. And now we're talking about representations on QP vector spaces, and QP is given the p-adic topology. So this construction is essentially going to only be well behaved on representations that are continuous in the much stronger sense that they're continuous if you give QP the discrete topology. So let's try to do a little better. So let me write C for the p-adic completion of K bar. Or the K bar has a ring of integers, so that's not ring that's not p-adically complete. So you p-adically complete it, and then you invert P. And this gives a field which, in the case where K is QP, it's sometimes called the field of p-adic complex numbers. It's some kind of non-Archimedean analog of the usual field of complex numbers. And you can do the same construction as the previous slide, except rather than using K bar, you use this bigger field C. And that bigger field gives you a better chance of finding invariants for the action of the Galois group. So taking these invariants again gives a finite dimensional vector space over K, and it's a little bit better behaved. So for example, this construction is going to see all unramified Galois representations, but it's not a lot better. You should again think of this as a construction that's almost always 0. So let me give an example of something that you miss when you do this construction. So this field K bar is algebraically closed. So for every n, we can choose a primitive p to the nth root of unity in K bar. And then you can look at how the Galois group acts on these roots of unity. So if you have an element of the Galois group, it'll carry a p to the nth root of unity to some power of itself. And as you record these powers, you get a homomorphism from the Galois group to the units in the p-adic integers. So this is called the cyclotomic character. And you can think of this as a Galois representation. Or for every integer n, you make a one-dimensional Galois representation, which is just a one-dimensional vector space over QP with a generator E, where the Galois group is acting on that generator by the nth power of this cyclotomic character. So these are called Tate twists, typically denoted by QP of n. And more generally, if V is a representation of the Galois group, I'll write V of n to mean V tensored with this Tate twist. So warning that if you take one of these representations and tensor it with C, you won't find any Galois invariants. These are still interesting representations even after you tensor with C, as long as n is not equal to 0. Okay, so let's talk about the kind of Galois representations that we might actually be interested in. So let X be an algebraic variety over K. I'm going to write XC to mean you take this variety and you extend scalars to the algebraically closed field C. And then you can study the Étale cohomology of that variety XC. And in your favorite degree, you get a finite dimensional vector space over QP, which is equipped with a continuous action of this Galois group G. And these representations can look very complicated and interesting, but you might try to simplify them by tensoring with the field C. So I'll write Hn of XC with coefficients in C to just mean this tensor product, which again has an action of the Galois group. The Galois group is now acting on each factor. And these are semi-linear Galois representations over C. They're vector spaces over C with an action of the Galois group that's compatible with the way that they act on C. And these are much more tractable objects, but they can still be non-trivial. And so an example to keep in mind, the fundamental example is to take X to be the projective line. And if you look at cohomology in degree 2, you'll find a one-dimensional vector space over QP, but it has a non-trivial action of the Galois group. The Galois group acts by the inverse of the cyclotomic character. And if you tensor that with the field C, you get something which is still a little bit non-trivial as a semi-linear Galois representation. So these Tate twists of the previous slide, they definitely come up in geometry. Okay, so this is the kind of thing that can come up. What else could come up? What could you say about representations that arise this way? So let me just start with just a brief remark about Hodge theory over the complex numbers. So if X is a smooth projective variety over the complex numbers, if you're interested in the complex cohomology of X, it has an interesting feature given by its Hodge decomposition. The nth cohomology group of X splits as a sum of n+1 pieces, which can be described in terms of coherent cohomology of X with coefficients in differential forms of different degrees. And so you could ask if you see some analog of this phenomenon for varieties over K. And this subject really starts with a paper of Tate from the 60s, who studies this situation in a special case. So Tate studied the situation where X was an abelian variety over K with good reduction, and showed that if you look at the first cohomology group, tensored with C, then it has something like a Hodge decomposition. It splits as a sum of two pieces, where one of those pieces has to do with the coherent cohomology of X, and the other one has to do with differential forms on X, and that appears with a twist by the cyclotomic character. So this is a statement about abelian varieties, but it immediately implies the corresponding statement for algebraic curves with good reduction. So you should think that Tate discovered some kind of one-dimensional version of a Hodge decomposition in p-adic geometry. And he asked if this was a general phenomenon. Could there be a similar Hodge-like decomposition for the Étale cohomology in all dimensions, maybe for varieties with good reduction, maybe even all varieties, or maybe even rigid analytic spaces that are not varieties? And this was a question for a while. It was resolved in the 80s by Faltings. So Faltings showed that for any smooth projective variety over K, there is a decomposition like this, namely the Étale cohomology with coefficients in C splits as a sum of pieces that look like differential forms of degrees, different degrees, with Tate twists appearing in the same twist by the corresponding power of the cyclotomic character. And so this is called the Hodge-Tate decomposition because it looks kind of like the Hodge decomposition for complex varieties, and because Tate was the first person to discover this phenomenon. This was extended to rigid analytic varieties, as Tate predicted by Peter Schulze about 10 years ago. So motivated by this theorem, let's introduce a bit of terminology. So let V be a representation of this Galois group. We say that V is a Hodge-Tate representation if, when you tensor with C, it's as a semilinear Galois representation that splits as a sum of Tate twists. So Faltings' theorem in this language is saying, in particular, that if X is a smooth projective variety, then it's Étale cohomology with coefficients in C is Hodge-Tate representation. Or, sorry, Étale cohomology of XC with QP coefficients is a Hodge-Tate representation. So this class of Hodge-Tate representations has good features. It's closed under tensor products, duality, subobjects, quotients. Warning, it's not closed under extensions. You can take an extension of two Hodge-Tate representations, which is not itself Hodge-Tate, and this is a point that we're going to come back to in the next lecture. So I want to say something about the construction of this Hodge-Tate decomposition. So it's something that you can break into two pieces. There's a story that happens just for varieties over C, which is an algebraically closed p-adic field that says that if you look at the Étale cohomology of a variety, that has a natural filtration where the successive quotients can be described in terms of Hodge cohomology, in terms of coherent cohomology with coefficients in differential forms. And then there's a second part which says that if your variety is defined over K, then this filtration actually has a unique splitting. And that's a sort of an independent story that just comes from understanding what Galois representations look like. In the world of semilinear Galois representations, these different Tate twists have nothing to do with one another, and therefore there can't be any interesting extensions between them. So I don't want to say anything about this second point, but I want to sketch for you a proof of this first point because it's very closely related to the constructions that we were talking about last week. So I just want to explain in the language of last week how this goes. So let's recall some of the constructions from last week. So let X be a projective variety over C. For right now, it doesn't need to be smooth. And let's choose an integral model of it. Let's extend it to some projective scheme over the ring of integers. And let me write X in Fraktur font to be the p-adic completion of that as a p-adic formal scheme. So last week, I talked about this construction that I called RH prism bar. And that takes Étale sheaves on this integral model and produces for you quasi-coherent complexes on that formal scheme. And I also told you about this finiteness theorem of Zavyalov that tells you that if you input something which is a constructible p-adic Étale sheaf, then you get out something that satisfies some finiteness. It's an almost coherent complex on this formal scheme. And now let me mention something that you can do with that, which is that these almost coherent complexes satisfy a Gaga principle. There's no difference between giving an almost coherent complex on the formal scheme X and on this integral model X bar. So as a consequence, all of these, if you apply this to a functor to a constructible complex of sheaves on X bar, what you'll produce is something that you can think of as an almost coherent complex that lives on the same scheme. And I just want to take this construction and invert P. If I take an almost coherent sheaf on X bar and invert P, I can think of that as now a coherent complex that lives on X. And this construction is completely insensitive to what's going on this for the input on the special fiber. Remember this functor RH prism bar, when you evaluate it on sheaves that live on the special fiber of X bar, it assigns complexes that are almost zero and then will be annihilated by this process of inverting P. So this gives you a functor that I'm now going to denote by RHC, because it's happening in the world of now just of varieties over C. And it goes from the category of constructible sheaves on Étale sheaves on X and produces coherent complexes on X. So what can you say about this? Well, first, what does it do when X is a point? So when X is a point, the left-hand side is the derived category of QP vector spaces. The right-hand side is the derived category of vector spaces over C. And this construction is the only thing it possibly could be. It just takes a vector space over QP and tensors it with C. Another feature which I mentioned last time is that this RH prism bar is compatible with the formation of direct images along proper morphisms. In particular, it's compatible with pushing forward from X to a point. And what does that mean concretely? Well, let's say you start with something that lives here. So it's some kind of constructible Étale sheaf on X. If you follow this construction in the counterclockwise direction, then what you'll do is compute the cohomology of X with coefficients in F, and then tensor that with the field C. On the other hand, if you follow the construction in the other direction, well, you first apply this mysterious construction RHC to produce some coherent complex, And then you take the cohomology of X with coefficients in that coherent complex. All right, so let's just take what I just said and apply it in the case of the constant sheaf. So then the left-hand side, you're describing the Étale cohomology of X with coefficients in C. And the right-hand side is the coherent cohomology of X with coefficients in some complex, whatever this RHC gives. And if you want this to be useful, of course, you want to know what that coherent complex looks like. So let's ask this question. So first, let me give a tautological answer. If you go back to the construction of it, how do you make this RHC? In this case, well, the prescription was to choose a formal model. And then that formal model has some structure sheaf, and you apply some perfectoidization construction to it. That a priori gives you some coherent complex that lives on a formal scheme, but you have enough finiteness that it naturally extends to something that lives on the integral model, which you can restrict to X. So that construction has a description directly in the world of rigid analytic geometry. So let X be a projective variety over C. Let me write calligraphic X for the associated rigid analytic space. And let me write OX plus for the sheaf of integral functions on it. So this sheaf of integral functions has the property that when you invert P, you get the usual structure sheaf of that rigid space X. And now if X is reduced, then this OX plus is a p-adically complete as an object in the category of abelian sheaves. But warning, it's not p-adically complete if you think of it as living in the derived category of sheaves. That is, if you take the reductions of OX plus mod p to the n and form their homotopy limit in the derived category, you get something which I'll denote by OX plus hat. And that's typically lives in many different cohomological degrees. It's no longer concentrated in degree 0. And that's what this RHC is doing on the constant sheaf. It's taking this OX plus, it's p-adically completing it in some derived sense, and it's inverting P. And at the end of that process, you learn that this is actually a coherent when viewed as a module over OX. And that's the object that we want to understand. Well, I've given you two answers, not really to the question I asked. I asked, what does it look like? And I just recalled the definition of it from 2 points of view. But what does it actually look like? So this gadget here, it's a complex with coherent cohomologies. So you can take its cohomology sheaves and ask, which cohomology sheaves do you get? And if X is a smooth projective variety, this has a very nice answer, which is due to faultings, which is that the jth cohomology looks like differential forms of degree J on X. And well, rough idea is that Faulting's almost purity theorem tells you that this is something that you can compute locally on X. And so you might as well try to figure out what it looks like in the case where not only X is smooth, but X has a smooth formal model. And then a sort of anachronistic proof would be that this object here was eventually defined in terms of some perfected version of prismatic cohomology. But when X has a smooth formal model, there's not that big a difference between prismatic cohomology, which is not perfected, and prismatic cohomology, which is perfected. The difference will disappear after you reduce modulo the ideal I and invert P. Of course, that theory of prismatic cohomology sort of postdates this calculation by quite a bit. So what's a consequence of this? Well, the Étale cohomology of X is something which is computed as the coherent cohomology with coefficients in this complex. And therefore, you get some hypercohomology spectral sequence, which the input has to do with Hodge cohomology. That is the cohomology of X with coefficients in differential forms and converges to Étale cohomology. And this spectral sequence has to degenerate and therefore give you the filtration, which I was asserting the existence of earlier, just by counting arguments. The dimension of the initial page and the dimension of the final page are the same. for example, because of classical Hodge decomposition. So I want to just put what I just said in context. Let's go back to the usual complex numbers. Let's say X is a smooth variety over the complex numbers, and say you want to understand the cohomology of X with coefficients in C. Well, you can compute that using the de Rham complex. You can compute that has something to do with differential forms, and that's a very useful thing to know. So that's responsible, for example, for the fact that the complex cohomology has a Hodge decomposition. And now, what is this Riemann-Hilbert functor from the first lecture doing in these terms? It's extending the usefulness of this tool. So let's say you weren't really interested in the cohomology of X with constant coefficients. Let's say you were interested in understanding the cohomology of X with coefficients in some other sheaf of complex vector spaces. Well, the Riemann-Hilbert correspondence will tell you that that can also be computed by a kind of de Rham complex. But now it's not the usual de Rham complex, it's the de Rham complex with coefficients in a certain D module. And lecture 2, that Riemann-Hilbert correspondence over FP, you can think about that in a similar way. So if X is an FP scheme, and you want to understand its mod P Étale cohomology, there's a standard method to try to understand that, which is to use the Artin-Schreier sequence. And I talked about this Riemann-Hilbert correspondence, and you can think about that as giving you an extension of the usefulness of that tool. That is, now suppose you don't want to understand the cohomology of the constant sheaf. You want to understand the cohomology of X with coefficients in some other p-torsion sheaf. Well, that's also computed by some kind of Artin-Schreier sequence, but now it's a twisted version that takes coefficients in a certain Frobenius module. And this Riemann-Hilbert correspondence tells you what Frobenius module to take. And so this Functor RHC that I'm describing here, it can be thought of in a similar way. Right now, we're in p-adic geometry. Let X be a projective variety over C. And suppose you want to understand its Étale cohomology with coefficients in C. Well, there's a way to reduce that to coherent cohomology by thinking about this OX plus p-adically completing and inverting P. And that's a useful observation, and it leads to this Hodge-Tate decomposition. And this functor, which essentially is a version of what we described last week, is designed to extend the reach of that tool. That is, it's now something which takes an arbitrary constructible sheaf on X and assigns a coherent complex that gives you a way of computing X or rewriting the Étale cohomology of X with coefficients in some Étale sheaf as a kind of coherent cohomology. So getting something like a Hodge-Tate spectral sequence with coefficients. All right, so I'm going to return to this in the next lecture, I think, but I would like to spend the rest of this lecture going back to the subject of p-adic Hodge theory and talk about another important facet of it, which is the de Rham comparison here. So let me say if we have a smooth variety over K, if you want to talk about its cohomology, well, there's at least two things you might mean by that. So one thing that we've been talking about is that you can look at the p-adic Étale cohomology of X base change to some algebraically closed field. But another thing, this is a finite dimensional vector space over QP, which is equipped with an action of the Galois group. But another thing that you might mean is the de Rham cohomology of X. You can think about an algebraic version of the de Rham complex and study the hypercohomology of X with coefficients in that complex. So that gives you a vector space called Hn de Rham of X. These are finite dimensional vector spaces over K. And a question that goes back to Grothendieck is, how are these constructions related? So first, let me say this question is subtle, because these are both constructions that give you vector spaces, but they're not even vector spaces over the same field. One is a vector space over QP, one is a vector space over K. And the first construction isn't quite canonical. It depends on a choice of algebraic closure. The second one is canonical. So the answer isn't just these are the same vector space. So to sort of get a sense of what the answer might look like, let me first talk about an analogous story over the complex numbers. So let's say X is a smooth variety. Well, in that case, you have an isomorphism of complex vector spaces, where on the left, you could think about X as a complex manifold and take its singular cohomology with coefficients in C. And that's equivalent, isomorphic to the algebraic de Rham cohomology of X. And this is really two theorems in one. Right? There's an identification of singular cohomology with the de Rham cohomology valued in smooth differential forms that goes back to de Rham in the 30s. And there's a theorem of Grothendieck from the 60s saying that if you have an algebraic variety, there's no difference between its cohomology with coefficients in smooth differential forms and if you use algebraic differential forms. So there's some isomorphism of complex vector spaces here. But now the vector space that appears on the left actually starts life as a rational vector space. As you can look at the singular cohomology of X with coefficients in C, but you could also look at the singular cohomology of X with coefficients in Q. And that's something that you can think of as giving you a Q lattice inside this C vector space. Now, if X was an algebraic variety defined over Q, then the vector space on the right has a similar story. As you can look at algebraic de Rham cohomology, that's some complex that has to do with polynomial differential forms. Here, the polynomials were allowed to have complex coefficients. But if X was defined over Q, you could restrict to polynomials having rational coefficients. And that actually gives you a rational vector space that this is the complexification of. And just a warning that there's an isomorphism of complex vector spaces here. Each of them comes from a rational vector space, but the isomorphism doesn't come from an isomorphism of rational vector spaces. So let's see an example. So let X be the complex plane minus the origin. So you can think about that as an algebraic variety, where you take the spectrum of the ring of Laurent polynomials. And this is naturally defined over the rational numbers because you can write down that Laurent polynomial ring over Q. So what does the singular cohomology look like? So if you compute cohomology in degree 1, that's just maps from the fundamental group of X into Q. So the fundamental group of X is it's just a free group on one generator corresponding to a loop that goes once around the origin. And that corresponds to a generator of this singular cohomology group H1Q, which I'll denote by V. And you can also look at the de Rham cohomology of this rational variety, X0. So that's a one-dimensional vector space over Q. It's generated by a vector V prime, which you can take to be the cohomology class, which is represented by the differential form dz over z. So in these terms, that once you complexify these vector spaces, they become the same by de Rham theory. And that isomorphism, it carries V prime to some multiple of V. And if you want to know what multiple it is, what you're supposed to do is take this differential form dz over z and integrate it around a loop that goes around the origin. And a basic calculation is that that gives the number 2 pi I or minus 2 pi I, depending on which direction you went. But note that this number 2 pi I is not rational. So this isomorphism is not happening over the rational numbers. Okay, so this is a story that you can tell a little bit more generally. So if X is any smooth algebraic variety over Q, you can look at some de Rham cohomology group, which is a finite dimensional vector space over Q, and you can choose a basis for it. You could complexify your variety, make something that's a complex manifold, and look at the singular cohomology. That's also a rational vector space you can choose a basis of. And then once you complexify these rational vector spaces, de Rham theory gives you an isomorphism. And in terms of those bases, that's some invertible matrix of complex numbers. And the complex numbers which can appear in such a matrix are called periods. And an example would be the number 2 pi I is a period. We found a 1-by-1 matrix on the previous slide that came from this construction. Okay, so getting back to p-adic geometry. Let's say we have a smooth projective variety over the p-adic field K. You can again look at these two vector spaces given by Rham cohomology and Étale cohomology with QP coefficients. They're not really the same. They're defined over different fields, but Fontaine's proposal for the way they should be related is that they should become isomorphic after you extend scalars to some bigger field, a field that he called B de Rham. And the heuristic idea is that B de Rham is some field of p-adic periods. It's some very large field that contains all the numbers like 2 pi I that you would ever see if you were to take an algebraic differential form and try to integrate it against a cycle. So that's a heuristic, but this ring B de Rham has a definition. Let me recall it for you. So first, this algebraically closed p-adic field C has a valuation ring OC, which is an example of a perfectoid ring. And remember that every perfectoid ring has a canonical presentation as a quotient A mod I, where A comma I is a perfect prism. And in this situation, the ring A is I-adically complete. It's the inverse limit of the sequence of rings A mod I to the n. You can take this inverse system of rings and just invert P everywhere and take the inverse limit of that. And that produces a ring which is called B de Rham plus. Now this ring A is not Noetherian, but this ring B de Rham plus is a little simpler. So Fontaine proved that this was a discrete valuation ring. And B de Rham is defined to be its fraction field. So let me tell you a little more about what this ring B de Rham plus looks like. So first of all, it's constructed out of a choice of algebraic closure of K, and this Galois group acts on everything that's involved at every stage of the construction. In particular, it acts on B de Rham plus. Now, B de Rham plus contains a particularly interesting element, which is typically denoted by T, on which the Galois group acts in a very simple way. It acts by the cyclotomic character. So if that element T is not Galois invariant, but it transforms in this way. And that element T you should think of as a p-adic analog of the complex number 2 pi I. Now, this ring B de Rham plus is t-adically complete. And when you reduce modulo T, you get the field C back again. And just as a consequence of that, if you want to know what it looks like as an abstract commutative ring, it's isomorphic to a power series ring on the variable T over the field C. But this is a very non-canonical isomorphism. This is the kind of thing that you can prove assuming the axiom of choice, but never actually explicitly exhibit. And then this B de Rham is the field that you get by taking B de Rham plus and inverting the element T. So that's a very large field, but it's also acted on by the Galois group. And if you take the Galois invariance inside that field, it's just the field K that you started with. Okay, so let X be a smooth projective variety over K. Fontaine conjectured that this B de Rham plus, which was defined by this algebraic procedure that I sketched to you on the previous slide, should play the role of some field in which all the p-adic periods lived. So more precisely, it should be such that if you take the de Rham cohomology of X and tensor over K with B de Rham plus, that's canonically identified with the Étale cohomology of XC tensored over QP with B de Rham. And moreover, I said it should be canonical. In particular, it should be Galois invariant. So motivated by this conjecture, let me just introduce some terminology. So let's say V is a representation of the Galois group on a QP vector space again. We say that V is a de Rham representation if when you tensor with this field B de Rham, it has a basis of G invariant vectors. In other words, it essentially becomes a trivial representation after you tensor with B de Rham. Or as trivial as it can be, given that it's a semilinear representation. And so related, this is a definition that's related to a certain construction, which I'll denote by D of V. So given a vector, your representation V, you can tensor with B de Rham, and then you can look at all of the Galois invariant vectors. And that's a vector space over the field K. And it's not hard to convince yourself that it's a finite dimensional vector space over K, and that its dimension is at most the dimension of the representation that you started with. And V is a de Rham representation if and only if the dimensions are the same. So this condition of being a de Rham representation is closely related to the condition of being a Hodge-Tate representation. So let V be a representation of the Galois group. This K vector space D of V has a natural filtration coming from the fact that the field B de Rham itself has a filtration. B de Rham was defined as the fraction field of a discrete valuation ring, and therefore it has a natural filtration given by the ideals given by the powers of T. And so we'll say that something lives in filtration I if it's a Galois invariant that lives in V tensored with this subset of B de Rham. And so something that you can prove, it's essentially like an exercise in understanding the linear algebra of these rings, is that if you take V and if V is a de Rham representation and you tensor it with C, then what you get is just the sum of the associated gradients for this filtration on D of V with certain Tate twists attached. And in particular, if V is a de Rham representation, then it's also a Hodge-Tate representation. Okay, so with this language, let me just restate Fontaine's conjecture. So X is a smooth projective variety over K. And if you look at its Étale cohomology, that's some representation of the Galois group. The conjecture is that's a de Rham representation. And moreover, when you go to extract when you tensor with B de Rham and extract the Galois invariant vectors, what you'll see is exactly the de Rham cohomology of the same variety X. And moreover, this is not just an isomorphism of vector spaces, it's an isomorphism of filtered vector spaces where you equip de Rham cohomology with its Hodge filtration. So you can think of this as a refinement of Tate's conjecture. If this representation is de Rham, then in particular it's Hodge-Tate. And if you know this at the level of filtered vector spaces, in particular, you know at the level of the associated graded what you're supposed to see. All right, so this conjecture was also proved by Faltings in the late 80s. And it was extended to rigid analytic spaces by Peter Schulze about 10 years ago. So I would like to just sketch for you the argument that Peter used to show this, because it's going to be relevant to the story that I tell in the last lecture. So first, a sort of heuristic of what we're trying to do. So Fontaine defined this functor from representations of G to filtered K vector spaces. The functor, remember, you tensor with B de Rham and then you take Galois invariants. And the sort of heuristic that's going to inform this is what the Riemann-Hilbert correspondence should be doing in the case where the variety is the point spec K. And in order to prove this comparison conjecture, what you want to do is extend the Riemann-Hilbert correspondence to varieties which are not a point. You want to have a similar construction for varieties that live over for smooth projective varieties in general. And the fact there should be some compatibility of these constructions with direct images that should specialize to the Fontaine's comparison conjecture. Okay, so how do you realize this? So let X be a smooth projective variety over K. calligraphic X is going to be the associated rigid space. Peter introduced a very fine topology on X called the pro-Étale topology. And he introduced a certain sheaf that lives on that sheaf with respect to that very fine topology. And that sheaf is kind of a relative version of the ring B de Rham. And there's a natural map from X with this very fine topology to X equipped with its Étale topology, say. And that's a map of ring spaces if you give the Étale topology the usual structure sheaf and the pro-Étale site this funny period sheaf as its structure sheaf. And you can use that to make an analog of Fontaine's construction. So let F be a local system on X. Then what you could do is take that local system, you restrict it to the pro-Étale site, and then you tensor with this analog of B de Rham, and then you push it forward back to X. Let me call that D of F. Let me emphasize, this is not a derived push forward. This is a push forward in the world of abelian sheaves, unlike, I think, every other time that I've written a lower star in this series of lectures, when there's been implicitly derived. Right, so this is a construction, and this produces for you something which is an OX module, which is equipped with a filtration and with a flat connection. And it's a generalization of Fontaine's construction. If X was just spec K, this would be the usual construction of Fontaine that takes a Galois representation and extracts from it a filtered vector space. And just as in the story over a point, you're worried a priori that this construction might just kill everything. And that you should expect that's the general behavior. But we'll be interested in cases where that doesn't happen, where this push forward construction is sort of large enough. So let F be a QP local system, let E be this associated OX module with flat connection. Definition, we say that the local system is de Rham if this is a filtered vector bundle, and moreover, when you pull it back to the pro-Étale site, it just recovers your original local system back again, tensored with this period sheaf. And again, this is something that when X is just a point, recovers Fontaine's definition. This was definition of de Rham Galois representation. And now the point, let's say you have a smooth projective variety over K, and you have a local system which satisfies this condition. So there's some associated filtered vector bundle now with a flat connection. And then you show that in this situation, there's some compatibility with taking cohomology. That is, you can take the cohomology of F in the world of Étale sheaves. If you tensor that over QP with B de Rham, then you'll recover the de Rham cohomology of X with coefficients in this local system E. That would be a priori a K vector space, should also be tensored with B de Rham. So this more informal statement of this is that this construction D is something that's compatible with taking proper direct images, where on one side that's in the world of Étale cohomology, and on the other side that's in the world of de Rham cohomology. And this is very closely related to the analogous property of the functor that we talked about earlier in this lecture, this RHC. And so in particular, when you specialize this to the case where F is the constant local system, this is Fontaine's conjecture. So I want to take this to be the answer to the original question. So let's say X is a smooth projective variety over K. You could ask, what should the Riemann-Hilbert correspondence be for local systems on X? Well, there's this construction D, which gives you a functor from de Rham local systems on X to filtered vector bundles with a flat connection on X. And this is maybe not quite as nice a picture as you had over the complex numbers. Remember the statement over the complex numbers, there was an equivalence of categories. This functor is not an equivalence of categories. It's it's not fully faithful even when X is a point. When X is a point, on top, you're studying some kind of Galois representations, and on the bottom, you're studying something that has to do with linear algebra over K, and it's just hard to avoid the fact that the theory of Galois representations is more complicated than that. So this functor is not fully faithful. And another complaint that you might have is that it's not defined on all local systems. It's defined only on these de Rham local systems. And the definition of de Rham local system was essentially a local system for which this was a good idea. But it turns out that that's actually not as restrictive a condition as it sounds like. So let me mention two results about this notion of de Rham local system. So let X be a smooth variety over K. Let me assume it's connected. And let F be a QP local system. So a few years ago, Rochuan Liu and Zhenwen Zhu showed that this condition of being de Rham is a pointwise condition on a local system. Saying that F is de Rham as a local system is equivalent to saying that if you take the stalk of this sheaf F at any point, that's then a Galois representation of, a representation of the Galois group of whatever the residue field is at that point. If at every closed point you get a de Rham representation, then the whole local system is de Rham. And in fact, you don't even need to check this at every closed point. You can just check this at any closed point as long as X is connected. So the notion of a de Rham local system is it's not much more restrictive over a variety than it is over a point. And another recent statement now in the setting of local systems with QP bar coefficients is that if you have a local system which is irreducible when you restrict it to a variety over an algebraically closed field, then it's not far from being de Rham. It's automatically obtained by taking a de Rham local system and just twisting it by a character. And that character could be something arbitrary and very far from being de Rham. So the upshot of this is you should think of this class of de Rham local systems as being very robust. It's a very good natural condition to put on a local system with good closure properties. And for local systems with that property, we have this functor D that plays the role of a Riemann-Hilbert correspondence. And now let me just advertise what I'm going to do in the final lecture. I want to talk about what would happen if either your variety was not smooth or you were interested in sheaves that were not local systems. That is, what should replace this construction of taking a local system F and replacing it by D of F. All right, thank you very much.